Good morning, everyone. My name is Colin Carter. I'm a professor of agricultural and resource economics at the University of California in Davis. I'm also director of the Giannini Foundation of Agricultural Economics, which is a UC-wide institution. The objective today is to discuss the most recent scientific understanding of how climate change affects California agriculture and its natural resources. And I thank all of you for coming today. With me on the stage, on my left, is UC Davis Chancellor Linda Katehi. On my far right is Dr. Ben Santer from Lawrence Livermore National Lab. And next to me is Professor Steve Sexton from North Carolina State University. I'd like to begin by acknowledging all the support and help I've received. Professor David Zilberman from UC Berkeley and Steve Sexton were very helpful in terms of shaping the program and identifying the speakers. Julie McNamara, who works for the foundation, orchestrated this entire event. It was a tremendous amount of work, and like always, Julie did a wonderful job. Thank you very much, Julie. Stephanie Schoen and Diane Jellison have been very helpful with logistics and paperwork. I appreciate their help. And finally, we have Bob Kelly on the camera. Bob's our AV guy. Thank you, Bob. Let me tell you a little bit about the Giannini Foundation. The foundation was established in 1928, a few years ago, through a gift to the University of California from the Bank of Italy, which is now the Bank of America. The board of directors of the Bank of Italy wanted to pay its founder, Amedeo Peter Giannini, some of the profits. And he was a very generous man, and he said, no, I want that money to go to the University of California for the study of agricultural economics as it applies to California. So he was also a great visionary. Mr. Giannini was a very, very successful businessman in San Francisco, and I think it's fair to say that he was truly one of the 20th century California titans. His bank became the Bank of America in 1930, and by the 1940s, it was the largest bank in the world. The endowment has grown since 1928, and we use the proceeds to sponsor research on 3 UC campuses, Berkeley, Davis, and Riverside. Our focus, the economics of agriculture in California. So let me give you a roadmap of the program today. Chancellor Katehi will lead off the forum with her comments on climate change. Then we'll turn to Ben Santer. Ben is actually a very renowned climate scientist, and he will discuss the implications of climate change for California and link it to agriculture. Ben's session will be moderated by Steve Sexton. The first panel, after the coffee break, will be moderated by the California Secretary of Agriculture, Karen Ross. You may have read a couple weeks ago, the US administration released a climate assessment report. That report singled out agriculture, and it talked about the threats to agriculture from climate change. Secretary Ross's panel will address that issue. Then we'll go to the lunch outside in the rotunda. I ask you to return from lunch promptly because Governor Jerry Brown will address the forum at 12:30. So please be in your seat by 12:25. The second panel will be moderated by Professor Aaron Smith from UC Davis. That same climate assessment report said that the US is not doing enough to adapt to climate change. We know there's a serious lack of global policies to reduce global emissions. As a result, an industry like agriculture has little choice but to adapt. For instance, China's emissions of carbon will not peak anytime soon. It could be another 25 to 30 years. The climate assessment report also talked about water, and it forecasts a decline in stream flows and snowpack, especially important for California, reducing available water. Professor Katrina Jesso from UC Davis will moderate the third panel on water. Then late in the afternoon, we'll bring Greg Dalton to the stage. Greg is the founder of Climate One at the Commonwealth Club in San Francisco. It's a very high quality program. I encourage you to look at his website. Even better, attend one of his sessions. They're really top notch. That's where I first met Ben Santer. Greg will address the interesting question of why climate change doesn't seem to be a huge priority for US Congress, because it's not a priority for Americans. The polls show that less than 1/3 of the American public believes climate change is a priority. Just prior to the climate assessment report, the UN Intergovernmental Panel on Climate Change released its 5th assessment of the science of climate change. They had some interesting conclusions with regard to agriculture. They concluded that the worst impacts of climate change will fall on industries like agriculture. And they also pointed out that some of the most serious impacts of climate change will affect agriculture. I don't have to tell you that we all live downstream from agriculture. Agriculture is clearly the canary in the coal mine when it comes to climate change. That's why we are here today. And I'm pleased to give you Chancellor Linda Katehi.
Thank you. Thank you. Good morning to everyone. Thank you for inviting me this morning to the conference organized by the Giannini Foundation on climate change. And of course, we all know how critical climate change has become to the economy of the state of California. Of course, its impact, as you very well described, to agricultural and natural resources. The foundation, as you said very well, has a very long history and tradition in our state, and of course that has translated into great work by the faculty and students of the University of California on the Davis campus, Riverside, and Berkeley. And of course, there are many more now, of course, universities and campuses also under the California State University system, where faculty and students study and try to understand, of course, the impact of climate change on agriculture, but of course they try in the process to make agriculture more affordable and food at the end accessible to people. There are a lot that we can say today, and I'm sure you will hear from experts on climate change and its impact on agriculture. What I would like to say is that not everyone understands agriculture or its science, which nowadays has become really the driving science in the 21st century. But everyone understands about food and about water and about quality of life. And what we have seen on our campuses are students who are coming to learn more about food because they worry about our ability to feed our own people, not just in the state and in the US, but around the world. Even the layperson understands that food can become very expensive when climate change can reduce production, and when it becomes very expensive then to transport food from one place, even in the US, to another, from one state to another. People do worry about the availability of water, and they do understand that both food and water are fundamental to improving quality of life, or even to sustaining the quality of life that we have been used to. So we as the University of California see ourselves as having a major goal and a mission to participate in trying to understand climate change, to educate our public about climate change, because as you heard, not too many people understand it. And there are many who do not believe in it. Fewer, of course, than I can remember in the 80s when we had major disagreements about climate change. At least the scientific world now seems to be more in agreement about climate change. But there are many people who do not understand it and in the process may not believe in it. And so we have a tremendous opportunity to educate the public, to use science to inform policy, and through conferences like that, find ways to not just understand climate change, but to use it to benefit agriculture and, of course, provide the opportunities for accessibility to food and water. There are a few faculty I would like to mention this morning for their great work in this area, and I will start with Colin Carter. Colin has been doing work in this area since many of us remember. He has been an international leader and expert on agriculture and resource economics, and being the director of the Giannini Foundation, he has helped organize many conferences and one today, of course, on this very important topic. And so I would like to thank you, Colin, for organizing this conference and for all of your work in this area. I would also like to mention Jan Hopmans, the UC Davis faculty in our Department of Land, Air, and Water Resources, who is the president of the Soil Society. And for those of you who may have spent a little bit time in the Dickett exhibit on the secrets of soil, this is an exhibit here in the museum that was designed by the Soil Science Society of America and the Smithsonian Museum of Natural History. And this exhibit is trying to help us understand the impacts of climate change in issues related to soil. And of course, for us Californians, these issues are very important. Jan is doing work on the impacts of climate change on the Central Valley soil and groundwater salinity. And I don't know whether he's here today, but he has been a great faculty member who is leading in this area through his work and the work of his students. We also have many more. UC Davis has about 2,000 faculty. And we have a great group of individuals who have been working on all aspects of agriculture and food, the environment, sustainability, and climate change. And it would take many hours today if I were to just mention a few of their major achievements, but I wanted to say that we as a campus are really very proud to have all of them and to enumerate so many of their achievements that have been so important to the agriculture in the state for many, many years. We have also created partnerships with Lawrence Livermore National Laboratories to be able to analyze and understand climate change, and also Lawrence Berkeley National Laboratories. And with both laboratories, we try to collaborate and find ways to use our computational models, to use our science, and to try to understand climate change, of course, as it expresses itself in California, but also around the world. Now, I don't want to say much about the impact of climate change. I'm not an expert, of course, in this area. You will hear a lot more from the conference today. But I wanted to mention that we are, in addition to the work that we are doing on our campus, we are also collaborators with other institutions, and there is one such collaboration that is major because it involves 6 institutions that make up the Southwest Science Climate Center, which is housed at the University of Arizona. Mark Swartz, who is director of the UC Davis John Muir Institute for the Environment, is an expert on the effects of climate change on plants and one of the principal investigators at the Arizona Center. Also, we have participated through the work of our faculty in policies that the state has adopted, and I would like to mention the AB 32 and, of course, the California's Cap and Trade program. And our faculty member, Dan Sperling, and his team have participated in developing these policies and also in trying to establish the science behind California's low carbon fuel standard. We know that these are very important standards and policies that will help our state mitigate the changes we have because of climate change. With that, I would like to also conclude by thanking our team, and I know that the governor is coming here today, and Secretary Ross is going to be here. Obviously, this is a very important conference, and I'm very pleased to see that you have been able to bring the leadership of the state to talk about the impacts of climate change.
Thank you, Chancellor. Stephen.
Great. Well, I suspect, like many in the room, I rely on climate science to inform my research agenda and to inform my research. And so I'm quite pleased that we have one of the foremost climate science experts here to help tell us about the state of our climate and the state of climate science. So, Dr. Santer, let's start with the big picture. The Intergovernmental Panel on Climate Change earlier this year released its 5th assessment of the physical science basis. And it determined that quote, the warming of the climate system is unequivocal, and since the 1950s, many of the observed changes are unprecedented over decades to millennia. What kinds of changes in our climate are we seeing?
First of all, good morning, ladies and gentlemen. Thank you, Colin, for this extraordinary opportunity to be here today. The 5th assessment report concluded that when you look at the changes we've observed in the climate system, they're everywhere. They're pervasive. And there's this amazing internal and physical consistency to the changes. We see warming of the oceans. We see warming of the land surface, retreat of Arctic sea ice, moistening of the atmosphere, rise in sea level, melting of glaciers over land, melting of the Greenland and West Antarctic ice sheets. We see change everywhere we look, and these things are monitored by independent instruments, monitoring platforms. Our understanding of the reality of climate change in observations does not rely on one record alone, as critics have contended. In the last couple of years, folks have argued, well, we really only understand about warming from looking at surface thermometers, and they're not very reliable. That's simply not true. Again, our understanding of all the changes I just mentioned in ice, in the ocean, on the land surface, in the atmosphere, relies on information from satellites, in situ measurements, from many, many different organizations around the world. That's the thing that gives us as scientists confidence in those words that the IPCC used, unambiguous warming.
So they say that some of these changes haven't been observed in millennia. We haven't had satellites for millennia. Where do those kinds of assessments come from? Indeed, much of the science is piecing together innovative data sets, right? But what kind of measurements do we have going back that time to inform those kinds of determinations?
Sure, and that's obviously a key question. How do we understand the changes I mentioned in the context of the past? Where do we get that context from? Well, let's look at atmospheric CO2 first. Currently, we're very close to the historic threshold of 400 parts per million carbon dioxide in the atmosphere. That's roughly a 40% increase since the Industrial Revolution. Now, to look at the deep past, we only have actual measurements of atmospheric CO2 since the late 1950s. Scientists have very cleverly looked at ice cores in Greenland and in Antarctica. And what they do is they look at bubbles of air trapped in glacial ice, and it's a natural time machine. By going back deeper into the core and extracting the air that was trapped in the bubble at the time it was formed, they can now go back nearly 1 million years. And from that, we understand that normal fluctuations in levels of atmospheric CO2 are from roughly 170 parts per million to 300. So we're well above anything we've observed in the last 1 million years, according to our best understanding of CO2 measured in ice cores. Look at temperature. Now, it'd be wonderful if we could retrospectively instrument the Earth and go back before the 1800s, since the first temperature measurements were made at major cities. We can't do that. But people can look at these indirect recorders of temperature, at organisms or animals and plants whose changes are related to changes in climate. Tree rings, the density, the width of tree rings, corals and their growth patterns over time, sediment cores and the abundance of diatoms, for example, in sediment cores. All of those things are proxies, as we call them, indirect recorders. And that kind of proxy information enables us to go back probably a couple of millennia for individual types of record. And that's what led the US National Academy and the IPCC to conclude that the warming that we've observed since the 1950s is highly unusual in the context of what these indirect recorders tell us about climate change over the last 800 years to probably a couple of millennia.
So while not universal agreement, there is broad agreement that the Earth is warming. The tricky part, it seems, comes in determining the cause of that warming. And so the IPCC determined that it's extremely likely that humans are the dominant cause of rising temperatures since the 1950s, and therefore predict that temperatures will rise by 0.3 to 4.8 degrees Celsius by the end of the century. How do they know that humans are causing most of that warming since the 1950s? How do you know?
Right, and going back to that statement, extremely likely had a specific probabilistic meaning in IPCC language, greater than 95% probability of occurrence. So how do we know? How do we know that the lion's share of that warming since 1950 is due to human activities? Well, let me back up and say, first of all, that we know beyond a shadow of a doubt that the burning of fossil fuels has changed the chemical composition of the atmosphere. That's a mutable fact. That's not a belief system. How do we know that? We know by looking at isotopes of carbon. When you burn fossil fuels, that burning has a specific isotopic signature in lighter and heavier isotopes of carbon. You can also look at the abundance of oxygen in the atmosphere. Very, very beautiful detective work done at labs around the world. And those isotopic measurements tell us that roughly 80% of the increase in atmospheric CO2 since the Industrial Revolution is due to human activities, the burning of fossil fuels. The other 20% is due to human-caused modification of the land surface, cutting down forests, doing things like that. So the real scientific question has always been not, are humans influencing climate, but how large is the climate change that arises from these human-caused changes to levels of heat-trapping greenhouse gases in the atmosphere? That's always been the real key question. Now, how do we look at that? Well, it turns out that we know a lot for centuries now about the physics of greenhouse gases, how they actually trap heat in the atmosphere. We've studied them in the lab. We can study them on other planets where there are greenhouse gases. So we know a lot experimentally and from basic physics about the properties, the heat trapping properties of greenhouse gases, what wavelengths they absorb at. People spend their scientific careers looking at these things. We know a lot from the observations about what climate change has actually occurred, what the manifestations are in ice, in snow, in temperature, in moisture. We know a lot from computer models of the climate system. These complex computer models are the ultimate Gedankenexperiment. You know, Einstein was fond of thought experiments that you could perform in your head, but not in the real world. Computer models of the climate system are the ultimate Gedankenexperiment. You can change one thing at a time, only human-caused changes in greenhouse gases, and see what is the impact of that. You can change purely natural factors, the sun, volcanoes, and study the impact of those changes. Very, very powerful for trying to figure out the individual signatures or fingerprints of different factors, natural and human, that affect the climate. And finally, we put the observations and the modeling together by doing fingerprinting. Fingerprinting is essentially signal processing. You're looking at these computer model simulations, say, which only involve changes in human influence over time, CO2, land use, particulate pollution. You look at the patterns of climate change that these computer models project, and you compare them with hard observations to try and see, are changes in the sun consistent with the changes we've seen in climate? Can the sun explains everything fit the bill? Does it cover all of the available observational evidence? Could internal cycles in the climate system explain the complex patterns of change that we see? And I'll give you just one example here of what I mean. And this example looks at the atmosphere, and it looks at slices of temperature through the atmosphere in these beautiful satellite observations that we've made from space since about 1979, and in the latest computer model simulations, the same simulations that fed into the fifth assessment report of the IPCC. And in the bottom panel, what you see are these satellite observations. Beautiful, beautiful things. They look at the microwave emissions of oxygen molecules, and those emissions are proportional to the temperature of broad layers of the atmosphere. These were made by colleagues right here in California, in Santa Rosa, the premier organization, really, in the world for doing microwave remote sensing of atmospheric temperature and atmospheric moisture. And what you see is that over 1979 to the present, the lower atmosphere has warmed and the upper atmosphere has cooled, consistent with our basic understanding of the heat-trapping properties of greenhouse gases. You can also see, looking at this picture here, that there's been profound warming over the lower atmosphere, over the Arctic, and that we've changed over the last 34 years, the period of satellite record, the relationship between the tropics and the Arctic. We've had much more warming of the Arctic, in part because of things called feedback mechanisms involving snow and ice relative to the tropics. That's changed the large-scale atmospheric circulation. Scientists have witnessed this expansion of the tropics, changes in the location of the jet stream over the last 30 to 50 years. And the model simulations, next please. Oh, that's me, actually, sorry about that. The model simulations that I mentioned are consistent with this when you include human influence. They also show this warming of the lower atmosphere and cooling of the upper atmosphere. Now, if all warming were solely due to an uptick in the sun's energy output, more sunlight arriving at the top of the atmosphere, as some critics have posited, you'd expect to see heating throughout the full vertical extent of the atmosphere, from the stratosphere right down to the surface. That's not what we see at all. These satellite measurements Weather balloons tell us a completely different story of warming low down, cooling high up, that is fundamentally inconsistent with the hypothesis that the sun explains everything, or that all of the observed changes could be to internal cycles. We know of no internal cycles that can produce this large-scale warming of the lower atmosphere and cooling of the upper atmosphere. El Nino, Pacific Decadal Oscillation, you name it. Nothing can produce that specific, unique pattern of warming low down and cooling high up that we've observed. And that's where a lot of confidence comes from confronting computer models with hard observations and probing beyond one global mean number, the average temperature of the planet, but looking at these complex geographical patterns of climate change or slices through the atmosphere or through the ocean. That's what gives us the discriminatory power and tells us natural causes can't explain what we've actually observed.
And in my own research, I look at spatial and temporal patterns of changes, look at the data, try and explain phenomena, and you see that the data seems consistent with the theory, and you explain other theories away. The data isn't consistent with those theories, but you can't rule out that there isn't some combination of these other forces that could produce that same data. It's just not likely, right? Is that fair?
That's right. And the slide I just showed was from a paper where we looked at this very question. It was published last year. In all fingerprint studies, what you're doing is trying to determine whether the agreement between some model calculation of the changes you'd expect to see due to human influence and actual observations could be due to natural fluctuations in climate. Things like El Niños, La Niñas, essentially year-to-year or decade-to-decade random fluctuations in climate. So that's what scientists typically look at. Now, in the latest round of IPCC simulations, we have simulations that in addition to looking at those internal variability changes in climate, also look at changes in the sun, changes in volcanoes, according to our best understanding of how those changed from 850 AD through to the present. So you can do exactly what you said. You can ask, could some combination of changes in the sun's energy output, very large volcanic eruptions, and internal year-to-year and decade-to-decade climate variability plausibly explain the changes I just showed you in the lower panel? They can't. Again, no combination either of internal variability or internal variability plus the sun plus volcanoes can generate that very curious and very large scale and sustained over decades pattern of warming of the lower atmosphere and cooling of the upper atmosphere. So we try very hard to find alternative explanations for the observed changes, but none thus far fits the bill. The best, the most parsimonious, is human-caused changes in greenhouse gases, because again, it's basic physics that tells us when we increase CO2, we more effectively trap heat lower in the atmosphere. The upper atmosphere has to cool to restore radiative balance of the Earth. I prefer to shave with Occam's razor, and I like going for the simplest, most parsimonious explanation.
Let's talk about these models for a second.
Sure.
The latest IPCC report shows that observed surface temperatures are falling in the very low end of the range projected by these models. And indeed, we've heard much about the so-called stasis or hiatus, that the Earth hasn't warmed for 15, 16, 17 years or so. How do you explain the fact that the models seem to be running hot, and does that concern you?
Sure. Well, this has received extraordinary attention in the last couple of years. It's been the subject of congressional testimony. The hiatus, quote unquote, in global warming was something I first ran into when I testified in front of the now defunct House Select Committee on Energy Independence and Global Warming, where one of the witnesses made this claim: global warming stopped in 1998, and computer models of the climate system are incapable of simulating decade-long periods with little or no warming. Now, the witness did not provide any evidence to support that assertion, so after that hearing, we actually looked at his claim. Can computer models of the climate system simulate short, decade-long periods with little or no warming of the surface or the lower atmosphere? Unambiguous answer: they can. Why? What's going on here? Well, in part, this is a signal-to-noise problem. Global warming conveys a certain expectation that each year is going to be inexorably warmer than the previous year, and each location on the Earth's surface is going to be warmer. That never was our scientific expectation. Any human-caused warming signal arising from gradual human-caused changes in levels of greenhouse gases in the atmosphere is going to be embedded in the rich year-to-year and decade-to-decade noise of internal climate fluctuations. Everything I mentioned previously, this zoo of internal oscillations of the climate system that have nothing to do with human activities. El Nino, La Nina, Pacific decadal oscillation, Atlantic multi-decadal oscillation. So scientifically, our expectation always has been to see some signal emerging from the noise in fits and starts, with periods where there isn't much warming, with periods with accelerated warming, and that's exactly what we see in the observations, that complex behavior. So what's happening over the last 15 years? What's happening since 1998? First of all, 1997, 98 was one of the biggest El Niños of the 20th century. On average, El Niños warm the planet. So if you start off near this big warming spike and look forward, that's a little bit of cherry picking there. You're starting at a point to give you some relatively modest or minimal change. You can't do that. Again, as scientists, if you want to beat down that year-to-year noise of internal variability, you look at changes over long sweeps of time. That's how you get more reliable estimates of the underlying human-caused changes in response to slow, changes in greenhouse gases. An analogy, if you look at the minute-by-minute record of day trading on the Dow, you wouldn't use that to make inferences about long-term structural changes in the Dow. In the same way, it's impermissible to look at a very short, noisy period of record to gain inferences about the presence or absence of some long-term human effect on climate. So the hiatus is a fantastic and very interesting detective story. And it turns out that it's not a whodunit, it's a they-done-it. It's not only these internal climate fluctuations, it's also volcanoes. We and others have showed that since the beginning of the 21st century, there's been, as one friend of mine likes to call it, a swarm of small volcanic eruptions, over 80 with a volcanic explosivity index of 3 or greater. And the net effect of these things has been to partly offset human-caused warming. These volcanic particles reflect some portion of the incoming sunlight back to space and cool the planet. The sun had an unusually long and low solar minimum during the last solar cycle. That's part of the hiatus too. There's been an uptick in Chinese emissions of sulfur dioxide, another cooling influence from Chinese coal-fired power plants, another cooling influence over the last 15 years. The real scientific challenge is to reliably quantify the contributions of the sun, volcanoes, Chinese sulfur dioxide emissions, and internal variability to the phenomenon we refer to as the hiatus. But does it fundamentally negate our understanding of human-caused climate change? No, it does not.
How long would it have to continue before you'd be worried that there's something wrong in these models?
Well, we looked at that question too in 2011, and that's a difficult question to answer. We don't know how volcanic activity, for example, is going to continue to evolve. Just in February, there was a very large eruption, one of the largest of the 21st century, Kelut in Indonesia, which got sulfur dioxide and ash up to about 28 kilometers. That's another cooling influence. I would be concerned if for a 20 to 30 year period there was no warming. That would be concerning to me.
We've been talking about these models sort of in how well they can predict at a temporal resolution. Let's talk about a spatial resolution and drill down to...
Could I just jump in there again?
Please.
And one important thing is that the simulations we look at are not really predictions, they're projections. A prediction is what you do with a weather forecast model. You actually absorb, you ingest observations of temperature and other things, and then make a forecast. These models do not do that. These models do not assimilate observational information about temperature or rainfall. They predict those things. They actually start typically in 1850 or 1860 and then are run forward with changes in the drivers, changes in carbon dioxide, changes in particulate pollution, the land surface, the sun, volcanoes, and they generate their own rich internal variability that is not in phase with what we've actually experienced in the real world. So it's an important distinction. These model simulations that we look at are projections, not the kind of predictions that people look at in weather forecasts.
Great point. So we're here talking about impacts on climate change for California agriculture. What do we know about how California's climate is going to change as a consequence of global climate change? I think you have a slide to help us with that.
Yeah, I think it might be worthwhile to look at 3 slides from the IPCC's 5th assessment report of the global scale projections. And what I'll show you is for temperature, first of all. And these are results from 39 models on the top, in the blue 32 models. These are our best shot, the IPCC's latest, greatest simulations of the expected global scale changes in land and ocean surface temperature out to 2100. And there are 2 envelopes there. The red envelope is a sort of business as usual emissions scenario where we eventually arrive at 900 plus parts per million CO2 by 2100. The blue envelope is for models run with a much more aggressive greenhouse gas emissions reduction scenario, which arrives at an endpoint of only 420 plus parts per million by 2100. So very different worlds. And of course, we have some influence on which world we follow, which energy pathway we follow, which mix of energy we decide to use going forward. But for the business as usual, and that's the pathway we're on at the moment, we're actually slightly above in terms of emissions of carbon dioxide. The emissions envisaged in the 8.5, the red scenario there. The expected temperature changes, global mean, are from 4.5 to 8.5 degrees Fahrenheit by 2100. So that's a different world. And of course, those changes would be regionally different, but global mean, that's a huge number. California would be profoundly impacted by that. The next thing I want to show you are the projected rainfall changes. Again, these are for those 2 scenarios. These are projected changes out to 2100. The 2.6, again, is the 420 parts per million by 2100. And the 8.5 is the over 900. And what I want you to look at there is the hatching. So if you look at California, for both scenarios there, around our latitudes, there's a lot of hatching. What that means is that the signal-to-noise ratio is low, that the models are not in strong agreement about the projected changes. And that's where we are. That's the state of the science. Trying to reliably project rainfall changes for relatively small domains like the state of California is tough. But that being said, what I showed you before in the observations illustrates that we are changing the temperature gradients between the tropics and the Arctic that control the large-scale atmospheric circulation. So, in my opinion, and in the opinion of many other scientists, we will change the circulation of the atmosphere. That will have impact on storm tracks. It will have impact on the jet stream. And many people believe that we're now beginning to see the canaries in the coal mine, to use Colin's terminology, in atmospheric circulation. The changes that we expect to see with this broad redistribution of heat in the lower atmosphere. So we will be affected. Precisely how we will be affected in terms of rainfall, we don't know. But a very robust feature of these model projections is snowpack decreases. And that's primarily due to the warming. It's a thermal signal. So despite these differences in moisture and model projections of future changes, snowpack decreases. The level at which snow falls goes steadily upwards, and that has tremendous implications for California for our access to water when we need it most in the summertime. Another very robust projection that is going to affect us profoundly here relates to sea level. So again, the two emission scenarios here, 8.5, 2.6, these are our best current estimates from the fifth assessment report of the projected changes. For 8.5, those projected changes go from 20 to nearly 40 inches global mean. Now, arguably, these projections are already out of date. If you were following the news in the last couple of weeks, a couple of papers in Science showed that we have likely estimated the contribution of the West Antarctic ice shelf to sea level rise. There's very, very beautiful studies that look at the bedrock on which some portion of that ice sheet is resting, and they find evidence that we've reached or are about to reach a tipping point where loss of much of the West Antarctic ice shelf is now irreversible. If they're right, then these numbers here, which assume a much more modest contribution of the West Antarctic ice shelf to global mean sea level rise, are already out of date. And that's concerning because, again, the Delta, California coast, much of what we know and love here in coastal California will be affected by this. And again, this is real. It's happening now. The best estimate of the observed increase, historical increase in sea levels since 1900 is about 8 inches. That doesn't sound much, but think of Hurricane Sandy and think how that inexorable raising of the baseline influences impacts.
So I think we'll shortly, let me ask one more question, then we'll shortly go to questions from the audience. You said that we have strong signal about the thermal effects and therefore strong evidence that sea levels will rise and that will impact our coastline. I'm told that the front page of today's Sacramento Bee, the local paper, has a story about climate change causing increased forest fires. Seems to me that would be related to the precipitation as well as to thermal impacts. What do you think? What is the state of the science basis for that kind of a claim?
I'm not all that knowledgeable about forest fire issues. What I can say is that some Canadian colleagues have tried to do this sort of fingerprinting work with areas burned by forest fire. Now, that's much more difficult to do than doing the kind of fingerprinting I do with atmospheric temperature or the amount of moisture in the atmosphere because, of course, area burned by forest fire is not purely a signal of changes in climate, but there's also some management signal in there that you've got to try and separate from the pure signal arising from warming and changes in rainfall. Tough job. But their finding was that there likely has been some human-caused climate change signal in the areas burned by forest fire in Western Canada and Western US. You look at satellite imagery. I was in Tucson last year, and they're probably the people at the Tree Ring Lab at the University of Arizona who have done more to study areas burned by forest fires in the southwestern US. It's astonishing when you look at that satellite imagery and see the increase over time in the area burned. So it certainly is physically plausible to me that as we warm the atmosphere, you know, one of the things we expect to see is a longer fire season, as the governor mentioned this morning in the LA Times article in which he's quoted. That's exactly what we see. There's also a tendency for dry areas to get drier, wet areas to get wetter. There's considerable observational evidence to support that as well. So I think what we're seeing in terms of fire and many other things is not a vast scientific surprise. It's expected behavior. The same holds for extreme events, changes in the frequency and intensity of droughts. These are things that we expect based on our understanding of large-scale changes in atmospheric temperature, moisture, and circulation.
So I think at this point the doctor is happy to entertain questions from the audience, and Colin, there will be roving microphones.
Mm-hmm.
Yeah, just before getting to those questions, I wanted to say that in addition to being a climate scientist, I'm also a climber. I've spent much of my life since I was 18 at in these fragile, high alpine environments around the world, in the Alps, in the Himalayas, in the Rockies, in the Cascades. And over one human lifetime, I've seen profound changes. Some of the glaciers I stood on while I was in the Alps are nearly gone now. A couple of years ago, I had the privilege of being at Camp 18 in the middle of the Juneau ice field in Alaska. You stand there at 7,000 feet on Camp 18. Climate change is not academic. It's pervasive. You look in any direction and you see signs of glacial retreat. It's incredibly sad to me that these beautiful, wild, fragile places will be experienced in a completely different way by our children and grandchildren. And in addition to the scientific imperative to better understand the nature and causes of climate change and likely outcomes for the state we live in and love, I believe there is also a moral and ethical imperative to try and preserve these strange and beautiful places and many others for future generations.
Two microphones.
So I guess if you have a question, go ahead and raise your hand, and we'll make sure we get a microphone to you. While they're thinking about their questions, Doctor, let me ask you about, I think there are a lot of economists in the room who might have seen some news making by an economist colleague on the IPCC.
Right.
Rob Stavins at Harvard was a co-coordinating lead author on Chapter 11, I believe, of Working Group 3. And he, within the past week or so, made public a letter to leaders of the IPCC expressing concern that the production of the Summary for Policymakers, the 33-page document that most of us are familiar with, that it was too politicized. He describes how from 11 p.m. until 1 a.m. one night in Berlin, he was called into a room with government officials who, of course, must approve this summary. And he says that a lot of the language was, I guess, stricken from what he had written because there wasn't consensus among this group. And so he expressed concern that the summary for policymakers, not the underlying technical documents and the longer thousands-page reports, but that these summaries ought better be called summaries by policymakers. You've been a part of this process.
Yes,
what
I have.
do you think about that? And is this consensus building that goes into those summaries that, if the public consumes any of these documents directly, those are the summary. That's the document they're likely going to access. Is that sort of optimal? Is that?
Well, that's a great question, and I believe that Congress will take up this issue on May 29th. I've heard that they will be having a hearing, the House Science, Space, and Technology Committee on this very issue. You're right, I was involved as convening lead author of the Detection and Attribution chapter in the second assessment report of the IPCC back in 1995, 1996. And in November 1995, we had a meeting similar to the meeting you described in Berlin, so-called plenary meeting, where all the national delegates comprising the Intergovernmental Panel on Climate Change get together in a room and are typically there for 3 days, and they go through line by line and word by word the summary for policymakers. And the challenge is to get countries with very, very divergent views of the science and the economics to agree on that short 4 or 5 page document. Now, back in Madrid in 1995, most of the focus was on one sentence from our chapter: the balance of evidence suggests a discernible human influence on global climate. A sentence that I will remember until my final day on this planet. It's funny to think that no matter what you do for the rest of your life, one sentence will follow you to the grave, and that one will follow me. And the challenge at those meetings is to find a way of getting the governments of the world to agree on the science while still preserving scientific integrity. Now, back then, I felt we got it about right. There were countries, I won't mention names, wanting a much stronger statement than our cautious balance of evidence statement. There were countries that didn't want any statement at all, that didn't want a detection and attribution chapter in the report. So is it an optimal process for coming to some consensus about the science? I don't know. One could imagine a situation where the national academies of a number of different countries were the final arbiters of how well the scientists from dozens of different countries had represented the science. However, if it were the national academies arbitrating, would it have the same weight as if over 100 countries with very divergent views about the science and economics are the final arbiters? I doubt it. I seriously doubt it. So in the end, as a scientist, you have a responsibility to make sure that the science is fairly and accurately represented. If you believe that the political process at the final stage fundamentally misrepresents and distorts the science, you have the option of removing your name from the document. So I think that still, even today, the IPCC reports represent the best mechanism for communicating complex scientific information on the basic physical science, on impacts, on mitigation and adaptation to policymakers. Could it be improved? Possibly. But I did not see, and I do not see today, fundamental political interference in the scientific process.
Thanks. I think I saw some hands out here. Yeah, please.
The last time I was aware that atmospheric science.
Can you please state your name and your
My name is
affiliation?
Alan Hirsch. I'm an urban forester. The last time I saw atmospheric science influence massive global public policy was the ozone situation. Can we learn anything from how the science actually was implemented into public policy and, quote, beginning to save the Earth for this even bigger problem? What can we learn from that, and how is it different? How is it the same, and how is it different?
Great question. Well, back in the 1970s, pioneering scientists, Susan Solomon, Mario Molina, Paul Crutzen, and others recognized and understood the complex chemistry that led to the destruction of stratospheric ozone. And they issued a warning. And intriguingly, some of the same people who have spent a couple of decades trying to attack the science of human-caused climate change were the very same individuals who said, ozone hole, that's impossible, that's not happening, or it's all natural, the same sort of arguments. But the science was so clear and so compelling, and the key issue was there were economic alternatives. Companies like ICI and Dow figured out how to produce relatively cheaply alternatives that were not going to catalyze the destruction of stratospheric ozone. Alternative refrigerants, and instead of losing millions of American jobs, as critics had argued, this is the inevitable outcome if we do something about ozone depletion, these companies made a lot of money. So one difference was there was a clear solution to the problem. But still, the countries of the world had to get together, sit at one table, put aside differences in national self-interest, and negotiate the Montreal Protocol, which they did. Now, I think the difference here is, even though the science is clear and compelling, I would argue now just as compelling as it was back then in the late 60s and early 70s on the stratospheric ozone issue. There isn't as clear an economic alternative. But we're beginning to see that, I would argue. Countries around the world are recognizing that those individuals, companies, countries that figure out cheap, efficient, low-carbon energy sources are going to be the leaders of the 21st century. And as I see it, we have a clear choice here in California and in the United States. We can be either leaders or followers. I hope we decide to be leaders and to embrace this challenge and to recognize the economic opportunities inherent in it, as the last several California governors have done. I believe that even in Congress now, people are willing to listen. I feel that in the last couple of years, I've had extraordinary opportunities to speak to people who wouldn't have given me the time of day 5 years ago, who get this economic change, that the world is changing, and they can either adapt or go the way of the dinosaurs. So I'm cautiously optimistic that we will indeed look back at the stratospheric ozone issue and learn some lessons from it.
Thank you. My name is Rick Bennis. I'm a retired engineer and a volunteer with the Sierra Club Energy and Climate Committees. And I'm curious what your thoughts are relative to the increasing attention being given what's considered the minor gases, but more intense effect gases such as methane. It seems like their effect is growing with respect to the findings of science. Could you comment on that?
Sure. Well, a lot of attention has been devoted to methane in the last few years. There's concern about methane being implicated in one of these tipping points. Where does that concern come from? Methane released from thawing permafrost. So permafrost should be renamed impermafrost, in my opinion. The reality is that it's melting, it's thawing, and that's releasing methane to the atmosphere. Methane is a potent greenhouse gas, 25 to 30 times more potent than CO2. There's also methane locked up in semi-solid form in these clathrates on the ocean floor. And there's some evidence indicating that these things may destabilize and release large amounts of methane to the atmosphere as we warm the oceans. Now, do we know how close we are to very large-scale releases of methane from thawing permafrost and from these clathrates on the ocean floor? No. The IPCC fifth assessment report, in its assessment of the methane issue, argued that we can't say much about the, well, they did not feel it was likely that we would experience a rapid release of methane over the 21st century. They did say that with continued warming over the 21st century, we will continue to see methane release from thawing permafrost and from these clathrates. So that's a concern, because if you look back at these proxy records again, we strongly suspect that very large methane releases were implicated in some of these rapid temperature changes that we see in deep time. With warming, you get this release, and we don't know how close we are to that tipping point. I love the sentence from Wally Broker at Lamont: "Climate is an angry beast, and we're poking it with a sharp stick." And we poked it a lot, but where exactly that tipping point is for methane, for other things like the Greenland ice sheet, the West Antarctic ice sheet, we don't know, and that's terribly difficult to determine how close you are to these key tipping points.
The Chancellor has a question. Chancellor Katehi.
Oh, I remember you mentioned that there has been substantial increase in temperature and CO2 since the 50s, for example. And I remember when I was in grade school, we were taught that the Earth has about 2 billion or so people. We are close to 6 billion today. Obviously, that growth in population, especially growth in areas that are financially underprivileged, what kind of policies or programs there are in place to make investments in these countries and to allow them to really do the things we can afford to do here in the state of California? It is very difficult to find access to alternative energy sources in countries that really where the lowest cost is an old car that uses gas, and where, for example, to warm yourself you need to use sometimes coal, oil, many times, because it's the lowest cost. So how are we, with so many people, and many more, are projected by 2050? How are we going to manage that?
I don't know, and I'm not the best person to answer that question, but I would say that smart people are already on the job. Look at Ramanathan at the Scripps Institution of Oceanography in La Jolla. He's from India, and he's very familiar with problems arising from cooking over open fires. You have all this black carbon that is released to the atmosphere, and he spent much of his recent scientific career studying the climate effect of that black carbon. Now, he decided a little while ago that he would actually do something about it. So together with some other scientists, he developed these solar-powered cookers that he could take to these remote villages in India and actually show them, listen, use this. And they were produced at low cost, and they provided light. They provided, it wasn't only for cooking, but also for purposes of providing light. Those are the kind of solutions. Just This last week, there was this interesting article about the drinkable book, a book with pages that you could actually use to filter water in remote areas that have no access to to clean water. That the pages of the book could actually be used to purify water. Incredibly creative solutions that are low cost and can be transferred rather easily, I think, to large segments of the population that don't have the kind of advantages that we have. In my opinion, and again, I'm not really informed on solutions, maybe we'll hear more about that this afternoon, this is the kind of thing we need to do, and we need to encourage. The atmosphere does not respect national boundaries, so nothing we do alone is going to solve the problem. And in order to have an effective solution, we need to involve the entire world in that solution.
Thanks. We've got time for one more question that I see back here, and I'm going to ask the doctor to be quick in his reply because we're really just out of time.
Great. My name's Ben King. I'm with King Golden State Orchards, and I want to thank the Giannini Foundation for putting this on. Thank you very much. My question really is there any prediction about what the El Nino effect's going to have, what global climate change might have an El Nino effect? I mean, I've looked at it and it seems not to be clear, but it does seem we're predicting that we're going to have a warmer temperature, but I don't know what that means as far as El Nino and maybe possibility of flooding in California going forward.
I think you're right. I think the jury is still out on how large-scale warming of the atmosphere and ocean moistening of the atmosphere is going to modulate the statistics of El Nino and La Nina. There is some evidence suggesting that El Ninos and La Ninas may become more intense, but we can't really make, at this stage, I would argue, confident predictions about changes in their frequency.
Okay, thank you very much. Please join me in thanking Chancellor Katehi, Ben Santer, Steve Sexton.